we are in the middle of proving this theorem due to Razborov and Smolensky, that if PQ are different primes, say 2 and 3, then mod 2 cannot be computed using mod 3 in a constant depth Boolean circuit. So we break up the proof into two lemmas. First lemma says that ACC03 circuit can be captured or reduced to a polynomial of low degree, okay, where degree is 2l raised to d, d is the depth of the circuit, which will approximate the circuit. So it's an approximator with a good number of or fraction of inputs. Once we have shown this, then we will also show that mod 2 doesn't have this property. Okay, mod 2 doesn't have good approximators, and that will give you the result that parity is not in AC0. Okay, that's a major result with a very interesting proof technique. So proof of lemma 1, right? So approximator will be constructed by induction on the size. So suppose you are looking at a gate G at height h, and for its inputs you already have approximators. Well, okay, so for this gate G, the approximator that we will build or construct is called G tilde, and we want its degree to be 2l raised to h, and it should correctly compute G on most of the x's. So we'll do this gate by gate. So the first case is, G is a NOT gate. So say G is not of F. For some gate F at height h minus 1, one less height. So by induction hypothesis, F has an approximator polynomial f tilde, whose degree is 2l raised to h minus 1. So using this f tilde, can you get G tilde? It's very easy. You just want to make 0 1 1 0, right? So you can define G tilde to be 1 minus f tilde. So when f tilde is 0, this is 1, when it is 1, this is 0, right? So this is the NOT approximator. In fact, this doesn't make any mistakes. So obviously the degree also has not changed. And G tilde doesn't introduce any errors. Okay, so when it's a NOT gate, then induction hypothesis carries forward successfully with this induction step. What is the base case of this induction? Base case you can think of as the leaves, which are the variables. Obviously the polynomial will be the variable, right? So base case is fine, and when G is a NOT gate, you have this induction step. What happens when G is a mod 3 gate? So remember, there are 4 types of gates: NOT, mod 3, and OR. So let's second induction step is for mod 3 gate. So say G is computing mod 3, of k inputs, f1 to fk. These are k gates, input gates. So by induction, there exists an approximator approximators f1 tilde to fk tilde of degree 1 height less, right? So 2l to the h minus 1, which respectively they approximate fi tilde approximates fi well. So using this, what will be the g tilde? So g tilde has to be just the sum. Okay, so g tilde is just, you can take it to be the sum. So remember that you wanted a polynomial mod 3, right, over the field f3. So there are 3 field constants, 0, 1 and 2. So the problem is that this sum can also have value 2. So it is not really a Boolean expression, Boolean value. So how do you solve that problem? You just square it. And when you square it, then 0, 1, 2, all these values, they are mapped to 0 or 1. So now g tilde is Boolean. It will give you only 0 or 1 values on 0 and 1 input. So that is the correct choice, correct definition of g tilde. What is the degree? So degree is whatever it was before doubled. So it's definitely smaller than 2l raised to h. And g tilde's definition again introduces no new error. Because if g was 0, so mod 3 value of f1 to fk, if it was 0, then g tilde will evaluate to 0. If it was 1, then it will evaluate to 1. And if it was 2, then g tilde will evaluate to 1. Right? So 0 is mapped to 0, 1 and 2 is mapped to 1. So that's the correct polynomial. So that's the second kind of induction step. Let us now do OR gate. So say G is OR of KFIs. So value of G is 0 if and only if all the FIs are 0, otherwise it is 1. And you have by induction hypothesis polynomials Fi tildes. How do you compute the OR polynomial approximator? So you have seen before when we did arithmetization of formulas, Boolean formulas. So if you use that kind of arithmetization, what will you get? So naive arithmetization gives G tilde to be 1 minus product of 1 minus Fi tilde I1 to k. So this has the property that if when all the Fi tildes are 0, then this evaluates to 0, otherwise it evaluates to 1. So this is not introducing any error, it's correct approximator, but the problem is its degree has multiplied k times. Okay, we don't want degree to grow so fast. So we have to somehow reduce this k, but we don't control k. K will depend on the size of the Boolean circuit, right? There may be many inputs to OR. So we have to do something else. It increases the degree k times, which is too much. So here we need to use probability and approximation. So till now, in cases 1 and 2, we didn't need probabilistic method and we didn't need any approximation, but now we will use it because we cannot afford to compute OR exactly. So instead what we will do, we will just randomly pick FIs out of F1 to Fk. We will pick few FIs and arithmetize. So that's the idea. So pick a random set S and consider mod 3. Okay, so it's not or it's actually mod 3 that we are looking at. So pick a random subset and compute mod 3, right? Mod 3 has the advantage that in case 2 you have already designed a polynomial for it, approximator polynomial, and the degree of that was as required, right? It was not too big, irrespective of how big S is. S may even be k, of size k. But then there will be some errors introduced, right? Because when you are picking a random set S, maybe you were unlucky and all these values of Fi were 0. Fi equal to 1 was happening somewhere else and you missed that, right? So we have to calculate that probability. What is that probability? So for all inputs, probability over S non-empty subsets that you are choosing randomly, probability that OR equals this mod 3. This is high. The probability is half. Okay, so there is some success probability, although it's not too high, but what you can do is you can repeat this and then the error probability will reduce. You can pick S many times. Okay, so this will be a useful step. So how do you show that OR is equal to this mod 3 of a random set of FIs on half of the inputs? Well, so in simplest form, the idea is that suppose only one of the FIs was 1, the rest were all 0, right? So what is the chance that you will pick this FI which is 1, or what is the chance that you will not pick it? So you have to show that the chance is half, okay, of picking it or not picking it. So let us formalize that. if for all I fi x bar is false, all the fi's are false, then this happens with probability 1. So this is an easy case, right? X says when all the fi's are false, then clearly OR matches mod 3 function. Otherwise, consider the linear form L. So fi evaluated and a formal variable yi. So consider this linear form in the variables y1 to yk. Fi x bar are actually values, right? They are 0 or 1. We are thinking of them as 0 or 1. So false is equated with 0. This L is a non-zero element of F3 with the variables y1 to yk. Key thing is that it's a non-zero linear form mod 3. Why? Because one of the fi is 1, right? So when you pick fi's randomly and take a sum, that is same as setting yi's to 1 and the other yi's, yj's to 0, right? So yi's you can think of as being picked randomly 0 or 1. So just observe that probability of picking y bar randomly in the space 0, 1 to the k, but not 0. Probability that, so what is the probability that Ly bar is 0 or not 0? When you pick y bar randomly, value 0, 1, what is the chance that Ly bar doesn't vanish? So there is at least one yi which is appearing in L, right? So actually only look at those yi's that appear in L, and you are fixing them 0, 1. So say it was y1 plus y2, right? So when you randomly fix y1 and y2, the chance that it will vanish is only half, right? Because whatever you will fix y1 or whatever you will pick y1, y2 has to cancel it. So y2's value will get fixed. So chance of picking that value of y2 is half. Okay, so this vanishing, the event of Ly bar vanishing, the probability is half. I should take all the y bars. So this probability is exactly half. Since on fixing all yi's except one, the last one gets fixed. So out of two possible values, this last one can take only one. So that is 1 over 2. That's the probability. So in other words, the probability over S 1 to k, you are picking a subset. So the probability that OR matches right. So Ly bar, you are looking at that version. Okay, we are in the case where this is actually 1. So this OR is already 1, and Ly bar that we are looking at is those yi's such that I is in S. So that is sum sigma fi for these i's. This sum is equal to 1. This probability we have shown is half. This is at least half, which is what we wanted to show. That's our claim. So for OR being equal to 0, probability is 1. OR being equal to 1, probability is at least half. Okay, but this is success probability is only half, right? We want to boost it. So to boost the probability, we pick many subsets. S1 to SL, subsets of 1 to K. And for each SI we do this experiment. What is the experiment? That you compute the sum of these particular FIs according to the subset mod 3. So you will get L values. What do you do with them? You take OR. So basically if even one of them is 1, then you output 1. If all of them are 0, then you output 0, hoping that original OR Fi was indeed 0. So you consider the polynomial G tilde prime OR of sigma Fi tilde with respect to S1. So square that. So this OR is the polynomial that we have defined here in the beginning. Let's just remember this. So this OR is using G tilde. Okay, so use the G tilde type of definition of OR. So that will multiply the degree of these input approximators by L, because you are using L polynomial inputs here or L functions here. But L is small, so this is not a big blow up. Previously the blow up was by K, that we have reduced to L. So observe that degree of G tilde prime, this is at most L times 2 times whatever was the degree of Fi tildes, which is 2L raised to H minus 1. So we have the bound of 2L raised to H as required. How well is the approximator approximating. So for all x, probability that g tilde prime is not equal to or g tilde prime is defined by this randomly chosen L subsets. So that's what the probability is over. Once you have picked S1 to SL, g tilde prime is defined, well defined polynomial, and that value at x bar, that polynomial at x bar evaluates to something different from OR, right? What is the chance of that? So that basically means that S1 at S1 the mod 3 value was wrong, at S2 it was wrong, at SL it was wrong. Each time this happens with error probability half. So this error probability is less than 1 over 2 to the L. Which means so from this we can deduce that there is actually a good choice of S1 to SL such that this event happens. So we are swapping the quantifiers now. We are swapping x bar with the choice S1 to SL. So when you swap this, what you will get is that there exist subsets S1 to SL, okay, such that the probability now over x bars of this bad event happening this is equally small, right? So you just swap it. Intuitively, I mean you can formally prove it, but intuitively why this should be true is because if suppose so this being false means that for every choice of S1 to SL the probability is bigger than 1 over 2 raised to L, right, for every choice of S1 to SL. But then that will contradict this for all x bar claim above, okay. So it's basically an averaging argument. So we have deduced that there exists this good choice. So we should actually fix S1 to SL to this. And denote the corresponding g tilde prime as the final g tilde. Okay. So we have the property that degree of g tilde is at most 2L to the h and introduces errors less than equal to 2 raised to minus L fraction. So these many erroneous x's have been added during this design. Okay, so that completes the description of OR approximator. Finally, let's go to AND. G is AND gate. Say G is AND of FIs so you can apply not on this. So not of G is OR of not of Fi. And now what you will do is from Fi tilde you will define the approximator of not Fi, and then you will use the OR design or approximator design given above. That will give you approximator for G, which is G tilde. So we have reduced the question to cases 1 and 3. So we have covered all the gates, namely not, mod 3, or, and. The degree at height h of a gate approximator is 2L to the h, and the errors that we introduce, that error fraction is at most 1 over 2 raised to L. So let us write that. So by induction, the above 4 cases convert a circuit C to a polynomial of degree because the root has depth or height d, right? D is a constant. So that is the degree bound on the final polynomial. And the error is, so which disagrees with C on at most S divided by 2 raised to L. Remember that there are at most S gates, so every gate can add 1 over 2 raised to L fraction. So this S over 2 raised to L is the total fraction by the union bound. Okay, so in the space 0, 1 to the n, this is the fraction. So that is exactly the statement of lemma 1. Lemma 1 is proved that ACC0 circuit, whatever the Boolean function it computes, can be approximated by a low degree polynomial on a good fraction of inputs. Okay, let us now do lemma 2. What is the approximator degree for mod 2? So suppose f, which is a polynomial, agrees with mod 2 of x1 to xn, which is again a Boolean function, parity. It agrees on some inputs, say call it G prime, and has degree low degree, right. So mod 2 is happening for n variables, but the approximator has degree square root n. Now what we want to show is that for this low degree polynomial, g prime should be small. Okay, g prime cannot be, I think in the lemma 2 statement we had 99%, right. So we want to show that g prime is less than 99%. So yeah, this is a very nice statement independent of circuits. Right, this is actually a fact about just this parity function and its approximator. So the way we will show it is we'll first change the notation from 0 1 to a sign plus minus 1. That will be very helpful. So transform f to a g as okay, so what did we do here? So when yi is or y1 let's say is 0, then y1 minus 1 is minus 1, and when it is 1 then y1 minus 1 is 0. Okay, so gy bar we'll think about as plus minus 1. So for minus 1 plus 1, if you feed this in g, okay, so you are taking yi to be, let's say you take y1 to be minus 1, then what is y1 minus 1? It is minus 2, which mod 3 is 1. When you are taking y1 to be 1, then y1 minus 1 is 0, right. So actually we are converting 1 to minus 1, 0 to 1. And then you will compute f, which will come out to be 0 or 1. So we are adding plus 1 to make it 1 or 2, and 2 is minus 1. So that's what we have done. Okay, so g is a polynomial function that on values plus minus 1 evaluates to plus minus 1. So g has become plus minus 1, f was 0 1. Okay, so 1 goes to minus 1, 0 goes to plus 1, and we have converted f to g. The whole problem statement is now converted from 0 1 to plus minus 1. They are isomorphic functions. Okay, and degree has not changed. So degree of g is still less than equal to square root n. And on this, so let us also define g prime becomes g. So g prime was a subset of 0 1 to the n, which now will convert to some other subset g, in the new domain -1 plus 1 to the n. So on G, what is the property of, on big G, this subset big G, what is the property of small g? It is equal to the product, okay, because small g is supposed to be mod 2, the parity in the 0-1 setting. Now when you move to +1 -1 setting, then the parity is just product, right? Because if so previously if the number of ones was even, now that would mean number of -1s is even. So sign will come out to be 1, which is the previous 0. So let me write this clearly, that this equals on y bar in G. Okay, so that's the advantage of this transformation, that you get a product. Parity becomes just product. So intuitively, a degree square root n polynomial shouldn't approximate this G polynomial right. So square root n polynomials, degree n square root n polynomials should not be able to approximate this product of y1 to yn well. That's the intuition. So this is what we'll formalize. Okay. So how should we proceed with this formalization? So what we will do is we will use this fact that there is an approximator for G of low degree. There is an approximator of product y1 to yn. A degree root n polynomial, the degree root n polynomial G shouldn't approximate y1 to yn well, right? So the way we will formalize, we'll get to this is we'll use this low degree approximator G to convert more general polynomials and reduce their degree. So more generally, consider Fg the set of functions from this domain G to F3. Okay, and we will now prove something about Fg using small g. So consider this set of functions from this domain big G, taking values in the field F3, so 0, 1, 2 valued. Now the small g will give you some property on these functions, all these functions. So what you can do is any u here has a multilinear representation U as monomials yi, where big I is a subset of the variables. How many variables? N variables. Okay, so there is every U has a multilinear representation. Why is it multilinear? Basically, we are saying that these monomials yi's, there is no square dividing it. Okay, so the individual degree of yi is either 1 or 0. It cannot be 2. So why can we claim that? Because G is a subset of -1 plus 1. So we can use the identity yi square equal to 1 for all I. Okay, so the point is that your domain doesn't have 0. Your domain is plus minus 1 valued. So in particular, any variable yi, if you square it, you get 1. So hence, if your polynomial u, if there is any monomial with yi square appearing, you can replace it by 1. If there is a yi cube, you can replace it by yi, and so on. Okay, so individual degree of yi in u can be made 0 or 1. So hence it's a multilinear polynomial representation over the field F3. So ai's are 0, 1 or -1. So this will now help us together with small g. So what we can do is this small trick. So replace each degree greater than n by 2 monomial yi by g times yi See, you can do this because g times product yi, I not in I, is the same as product of yi for all I and this multiplier. Now, if you look at the same yi, then you will get in the product yi square, which will be 1, right? So what you are left with is only those i's which are in I. So we can write these monomials using little g in this way. What is the advantage? The advantage is previously when you had n by 2 or more than n by 2 yi's. Now previously you had something far bigger than n by 2. Now you will have almost n by 2, because the degree of this is this has degree less than n by 2 plus square root n. Right, because the set big I had more than n by 2 elements, so the complement has less than n by 2 plus the degree of G, which is at most square root n. So any monomial whose degree is more than n by 2 plus root n, the degree falls after this transformation. In fact, what we have proved is this nice property that for every u, every function u in big F big G, u has a representation of degree less than n by 2 plus square root n. So a small g will actually have an impact on all these functions, all the functions on this domain big G. So this is a strong property, right? What does this tell you? So this means that look at the size of Fg. How many functions can there be? So the number of functions is 3 raised to m, where m is the number of these low degree monomials. Right, so basically the function u in the representation, you have these AIs, right? They take 3 values potentially. And how many I's are there, big I's are there? So the number of big I's is m, which is this how many n by 2 plus square root n degree monomials are there. And each AI takes 3 values, so 3 raised to m. This is the maximum number of u's you can have. That's one thing. So let us estimate this m. So this m is equal to n choose I for all these i's. Right, so how many subsets are there of size I? That's n choose I. And instead of going all the way to n, we are stopping around n by 2. Right, so if you stop in the middle, then you get half of 2 raised to n. But since you might go up to n by 2 plus square root n, there will be more than half of 2 raised to n. It will be, you can show that it is 0.99 times 2 raised to n. Okay, do this as an exercise. So that is what m is. M is a fraction of 2 raised to n. On the other hand, Fg in terms of the domain G, you get 3 raised to size of G. So we are counting it in 2 ways. One is simply by the domain size of G, and so that gives you 3 raised to G many functions. The other is more complicated, which is by the representation of the function as a polynomial of low degree. That gives you 3 raised to m. So which implies that size of G is less than equal to m, which is less than fraction of 2 raised to n. So the domain cannot be large. Okay, That is what we wanted to show. So no polynomial of degree less than equal to square root n agrees with mod 2 on 99% of inputs. Let's just see that. So this finishes, this tells you that mod parity has high degree approximators, and the first lemma told you that ACC 0 has low degree approximators. So that's a contradiction. Okay, that is what, these are the two facts we have shown, with very interesting techniques, and this tells you that mod P cannot be in ACC 0 Q for P and Q different.